All right. Good afternoon. We're going to start. My name is Aaron Portnoy, and it's my co-presenter Cody Pierce, talking about Microsoft RPC auditing tools and techniques. I'm going to start off with a quick about us. We work for a company called Tipping Point. It develops intrusion prevention systems. We're out of Austin, Texas in the US. Our team handles pen testing, vulnerability analysis, patch analysis, a bunch of things like that, research, basically research oriented. You can keep tabs on us on the website above there, which contains our blog and upcoming advisories, published advisories, appearances, and other things like that. We are authors and contributors to the Sully fuzzing framework with my coworker Pedram Amini and I released at Black Hat. Spoke about at Blue Hat and at Black Hat Japan. Cody spoke at Black Hat about PyMU, which is a Python-based x86 emulator. And we're both contributors to the PyMay reverse engineering framework. So today we're going to talk about Microsoft RPC, some tool set that we've developed, different techniques we use to audit it specifically. I'm going to start off with why are we talking about RPC in 2007, because it's generally considered something that's fairly well known. We're going to talk about the history of MSRPC briefly, about some of the vulnerabilities it's had, some of the issues it's had, some of the mitigations Microsoft's taken. I'm going to go through how it works, both from a developer standpoint and down to a security researcher, an auditor, reverse engineer, how you would see it from that level. I'm going to go through some of the existing tools that are out there, and some of the issues with actually auditing it, all the steps. I'm going to walk through a quick audit on knowing nothing about an RPC service to being able to communicate it with our tools. And we're going to release the tools and do a demo on a CA product, actually. So we're going to start off with why do we care about MSRPC? It's been covered for quite a few years. The main reason we're still dealing with it, as you can see here, there's still bugs being put out. It's 2006, 2007, the Razman's DNS workstation, distributed file system, all bugs, high impact, and a lot of them are still fairly simple stack smashes, things like that, that actually aren't very hard to find. Another big bullet point here we have is talking about third parties that implement RPC. So you have Samba that re-implements all the Microsoft RPC services. You have Computer Associates, which implements a bunch of their own custom things. Trend Micro, which does a bunch and has several vulnerabilities that have come out in the last couple months in their RPC services. We've also discovered that many of the RPC services that Microsoft still has haven't been fully audited. In fact, we have 2 bugs that we found with our framework that we reported to Microsoft a couple weeks ago that are fairly simple, but you wouldn't have been able to find them if you can't marshal all the NDR data correctly. So there's still simple Microsoft bugs that are out there. And trying to audit Microsoft or third-party RPC is still pretty difficult because the representation of the data is actually extremely complicated once you get into certain levels of embedded structures and things like that. I'm going to go through all that in the next sections. So brief history of some of the bugs in RPC. RPC bugs in MSRPC go back as far as 1998. There's DOSes back up until then, and we go all the way currently to vulnerabilities that are still being released nowadays. As you can see, there's just a few on there. Just some of the important ones. You can see the MSO3026, which resulted in the blaster worm. There are a few other large ones. A few other issues that MSRPC's had: interface hopping, null sessions. Interface hopping is just an architectural flaw where you can reach specific services if there's any open endpoints. Just going to go over some of the mitigations that Microsoft's taken with that. They've created some architectural mitigations such as name pipe firewalls and null session restrictions. Currently, there's still problems with RPC in the fact that despite the architectural changes they've made to MSRPC itself, third parties can still do extremely bad things in their implementations. It's almost as if they have the mentality that people can't communicate with their services, so they don't care what they do with that. For instance, CA, Bright Store, if you actually search for vulnerabilities in that, you will find that there's an obscene amount. The demo we're going to do has an RPC service that has 400 different functions that are available, and none of the Microsoft ones even come close to having that many. Then you have stuff like the Novell print services, which a few bugs have been released this month, actually.
So just quickly to go over why this was, or RPC was originally developed. Client-server model for remotely calling functions. Sorry about that. What Microsoft did was try to provide a simple way for developers to do remote communications, forked it off the DCE standard, the Open DCE standard, and then Microsoft core services use a lot of that for communicating between domain controllers and other systems you may have in a network. RPC breaks down into, interfaces, opcodes, and things of that nature, and to effectively separate that, or to allow a developer to easily communicate between those, they've had created stub functions that have a format string how to call each function, and the programmer can just call through that as opposed to doing the marshalling himself. They do this by defining an IDL file, which is the different function arguments, the different data structures that are going to be used in each call. And then the communication layer, they provided TCP, UDP, SMB, name pipes, all these different transports to communicate between services. They also have an endpoint mapper to do lookups on what's available. Inside of an actual binary that handles RPC, they have, like I mentioned, a format string, and the format string is inside of the actual binary. It's hard-coded in there, compiled from the IDL, that tells each function how to marshal the data, which is important for us because when we rip that out of a binary, we're going to use the tools that will take the format string and convert it back into a more human-readable form. And you also have important structures to set up the RPC interface, define any sort of permissions or the transport and things of that nature, and then a dispatch table for each function you provide. And we'll show, like I said, a tool that will pull out all this information so that you can instantly, figure out exactly what's being provided. Some of the problems with auditing RPC, I think, all stem from the fact that Microsoft designed it to be, hidden away from the user, or the developer, so he doesn't have to worry so much about all the different data marshaling, how things going to be transported, things of that nature. So, what you have to do is locate any DLL or EXE that provides the RPC service, because that's what you want to target. It has all the functions inside of it. Retrieving the IDL information, like I said, there's tools that exist that will pull that out for you, but that's all based off the format string, which if you look in a binary and you're reverse engineering, it's kind of difficult to do it manually. Determining pipe names is, which interfaces and how you can communicate with them. You have to pull that out of a binary. It's sometimes difficult to figure out. And then determining any authentication. And then what we're going to focus on, and what our tool set focuses on, is a lot of the even lower level stuff, which is the NDR marshaling, how it is actually transmitted over the wire. You have all these, functions, data structures, unions, things like that have to be specifically packaged so that the service will unmarshal it properly. And the biggest problem is that, if you are not packaging this data properly, it'll get kicked back before you even get to the functions you're auditing. So if you're not spot on with how you package it and send it across the wire, it'll get rejected. You won't even get to touch all the functions that you're trying to audit. You'll see bad stub data is what actually the RPC exception that gets sent back. Debugging that can be a problem since anything that will import from RPC RT4, it'll actually call into it, and it's kind of difficult to figure out exactly through embedded structures which one was not packaged properly. And then domain or computer name requirements. Oftentimes you have to provide a printer that's shared, a share name, host names, domain controllers. You have to provide that information before you can even get to the lower level functions. Like I said, to pull out some of this IDL information, there's two tools that we have used. The first one is Unmiddle, Dave Atel. I think he's in the crowd over there. Based off a muddle, retrieves IDL information from the format strings in the binary, handles all the complex objects, basically reconstructs what was compiled down from a static binary so that you can look at all the different functions, parameters, structures, and things of that nature. There's a URL. The one we actually use the most is MIDA, and it does effectively the same thing. It's a plugin for IDA. You can open a binary, just hit Control F7, and it'll pop up all the different functions that are available. You can click through them and see exactly where the RPC traffic will go to if you pass the NDR marshaling. There's the URL. And some of the older tools that we just kind of wanted to throw up here, a lot of these are more for remotely querying pipe names and seeing what's available on a system. You have RPC dump, which everybody probably knows. Pulling interface, UUIDs. Then we'll go into our tool set and how we kind of, provide something to all this.
Okay, so essentially Cody had talked about the IDL file. IDL file is the interface description language. You can basically, like he said, tells you how you can communicate with it. It'll tell you it has this many functions, here are the structures, here are the opcodes, this is how you would deal with it. So because there's already tools out there that will give you, from a binary, will give you that IDL file, like unmiddle and MIDA, we decided to skip the process of actually pulling from a binary and instead lex and parse those IDL files into Python objects. So we wrote a lexer and a parser that will take an IDL file. It mainly was developed using MIDA. It works partially with unmiddle right now. Essentially what it'll do is it'll pull out all the opcodes, all the arrays, the unions, the structures. It will create Python objects for all of those. It'll link them together, and we have a library of NDR objects. NDR stands for network data representation. So that's the way that, for instance, a long value or a structure or a short or a character array is actually packaged for on-the-wire transport. So we have a library of NDR objects that specify how to marshal all that information so it'll be correctly unmarshaled on the other end. And you can also print out the byte stream. You can do all sorts of things like that. We use InPacket, which is from core, to actually transport the marshaled data across the wire. We extended its functionality a little bit to support context handles, which is the reason you can't audit a lot of the Microsoft-specific RPC services, and people haven't found the bugs in them because they haven't been able to, as far as we know, handle a lot of the context handle communication, whereby you will query one opcode, get a specific handle back that you need to use in order to query another opcode, and you wouldn't be able to call that other one if you didn't have a valid handle. Now, we also have tie-ins for the Sully fuzzing framework. It just allows you to fuzz any of the services that you may have discovered. So, using our tool set, you're basically going to provide an IDL file. At that point, you just say, parse this IDL. You get a Python list of UUIDs. For each UUID, you can step through all the opcodes. For every opcode, you can step through the elements. The elements could be a structure, a union, an array. It could be a base type, a long, a short, whatever the IDL file actually defines. And you can pack any of that and transport it over the wire. So for instance, if you had a random RPC service you wanted to audit, you could dump the IDL, pick an opcode, and essentially say, parse this IDL, and I want to call opcode whatever, and it'll send it over the wire, and you won't have to worry about any of the marshaling, which can get quite complex if you have a decent-sized opcode. I mean, you're talking about thousands of bytes worth of data that have to be exactly spot on. If you're one byte off, it will not even get to the function you want to audit. You can populate any of these objects with any data that you may want. For a string, for instance, you could give it a domain name or whatever the hell you want, essentially. We built a quick little GUI that we're going to show a little bit later, if we have time, that lets you kind of expand out all the NDR or all the IDL objects, so you can see the class hierarchy of whatever it is you're dealing with in a tree structure. The entire process takes about a second on the largest Microsoft IDL, being about 2,000 lines, which is the LSA service, and it will give you all of these objects ready to go, and you can talk to the service. Why is this useful? We're saying it's useful because the NDR marshaling process is extremely error prone, like I mentioned. If you're a byte off, you will not be able to talk to these services. And that's why some of the bugs that we've been dealing with, you would not be able to do by hand, or it would take you a long time to do by hand, and that's why a lot of those bugs are still turning up, because people are starting to do it. And this toolset makes it a lot easier. So, quick example. This is a byte stream you would have to write for just one of the smaller opcodes actually, in one of the Microsoft RPC services, and this is a few pages long, just to give you an idea. You would have to do this by hand, whereas any of these bytes being off will not work. And that's everything from padding to deferent pointers, all sorts of kind of complex stuff. I'm going to go over some of the supplementary tools that we've developed.